gonna take the next 5 minutes and we are just going to cover one topic that I think wasn't very clear. So give me just 1 second here. There was a problem. There was a question, I should say. I'm just trying to open that problem. Like I just open it here. Okay. So you can see on the screen here, that was one of the questions that I had in the test. I mean, some people were, I mean, like it was easy for most guys, but there was a few guys that has some issues with this. Okay. So this is the transformer that we have been using so far in the shop. I mean, like you did in the shop like 3 labs. In those labs that you did, you were using this type of transformer. I mean, you don't have access to that side. Okay? You only have access to that side, which is, in this instance, you can see that it's giving you that the primary winding is 120 volts. And then on the secondary winding, you have a center tap transformer. So you have 12 between line 1 to the neutral. And then you have another 12 between the neutral and line 2. On the schematic diagram here, we can see that the bridge rectifier is connected across line 1. Let me check, okay. Okay. The bridge is connected between line 1 and line 2, which means that the voltage input for the bridge rectifier is 12 plus 12 is 24 volts. That's your voltage input for the bridge rectifier. You can see that that is how it is connected. Now, when you have your 24 volts and you multiply by 0.9, okay, in order to get, I mean, this 24 volts here is your RMS voltage. Okay, this is your RMS. Also, the other name for the RMS voltage is the effective voltage. Now, having the RMS, which is the same like the effective voltage, you are going to take that voltage and you are going to multiply by 0.9. And for those of you that were not sure how much was the voltage, but still use the 0.9, I mean, out of the 5 marks, I gave you 1 mark. I couldn't give you the full marks because, I mean, it wouldn't be fair if we don't use the right values. And even in the description, for most of you on the description, it says that the input voltage was line 1 and line 2. Now, having the 24 volts times 0.9, the output voltage for the positive, okay, here we have the positive terminal and the negative terminal. That would be right on this side. That would be equal to 21.6 volts. That was your average voltage. That's the name of this, average voltage. Now, the average voltage that is being applied to this load is not more than 21.6 volts DC. Having this with a 10 ohm resistor, that would give you 2.16 amps through the resistor. Okay, and there was 2 other questions there, and I was asking also for the peak voltage of the DC rectified voltage. So remember, please, that this is a signal, okay? that is a full wave rectification, but it still has a ripple voltage and it still has a peak voltage right there. You know, that voltage right there is not 21. That voltage right there was 30 volts. How do we find that voltage? We take our 21.6 volts, which is the effective voltage in this case, and we divide by 0.707, and that would be equal to 30.55 volts. Okay. The last question was how much was the ripple voltage? So you would take in that instance your 24 volts and multiply by 0.43, and that would give you 10.32 volts for the ripple voltage. So I think that was the only question that was causing like some issues during the test. And I just want to make sure to put it out there as a review, because when you were going to have a problem similar to this called the final. It's going to be retested, and I'm hoping then that you are going to be able to pass with flying colors, because this is something, we should be able to see it, to look at an schematic diagram, and we should be able to see how the schematic diagram is connected and be able to do the calculation accordingly, okay? So why is that important? Because this is the same thing that you are going to get in the shop once you get back in the tools, and you are going to have to look at the schematic diagram, connect it, and then do all the calculations as well. You will have to do two things, the calculations and also all the measurements. So you are going to do, like two things at the same time, okay? Calculation and measurement, because you're going to be able to verify that everything that you measure is actually being able to be calculated effectively with the formulas that we have given you. Any questions about this before we move on? So, okay, so let's begin with SCRs. Thank you for your questions. What I'm going to do in this case is that we're going to do two things. Number one, we are going to look at a PowerPoint, and we are just going to cover a few slides. And also, I'm going to show you a demonstration using multi-sim where we are going to use an SCR circuit, okay? So we are going to be doing that as well. So this is the circuit that you can see on the screen that we're going to be getting into. And also, I'm going to show you the circuit with a push button so I can show you how an SCR works. And we are going to do the same circuit using, instead of a push button, a variable resistor. And also, we are going to use the same SCR with an AC source. So on the first two examples that I show you, we had a DC source. On that one, DC source, DC. So we are going to see today how an SCR works in a DC circuit and how an SCR works on an AC circuit. We are going to see both, and we are going to see the behavior of the SCR in both situations. Now, any questions about that?
Shouldn't that be chapter 62 for the industrial motors book?
Yeah, like in mine, it says chapter 61, but that's fine. If you didn't read it, it is okay. You know, you have a time to read it going forward. So we're just gonna go ahead and just cover the basics, okay? And then you can, read the chapter after our class. Make sense? Also, I'm gonna be posting online, not today, because I still gotta type everything on Iconestoga. I'm gonna be posting a quiz about SCR, and again, that quiz is not going to be full marks. It's only a practice quiz. So, okay, so can you see the screen well there?
Yep.
Yep, you can see it. Perfect. So as I already told you, we are going to discuss the operation of the SCR in a DC circuit and in an AC circuit. And also, like, draw the schematic symbol for an SCR. Something else that we are going to be discussing is, we are going to be discussing this briefly today, but we are going to, first, I want you to be able to see what an SCR is. And then later, we are going to be getting into phase shifting, okay? Also, what is the test of an SCR with an ohm meter? How can you test it? And which type of test can be done on an SCR? And then we are going to be connecting, and that's a part that we have to do in the shop. But in our case, this is the multi-sim simulation that I just showed you, connecting an SCR in a circuit. So let's get started, okay? So when we are thinking about one SCR, we are thinking that we have pretty much two diodes connected back to back. So instead of having, remember that the diode, it is a PN junction. Okay? I want you please to remember that our diodes, they are a PN junction. Now, in the case of the SCR, instead of having just one diode, we have like two PN junctions connected back to back, okay, or connected in series. So again, this side is going to be called the anode. And this other side here, of course, because it's the negative, is the cathode. I'm just going to write for now cat. Oh, KTH. And right here, we see that we have a new pin. This new pin that we have on the SCR is called the gate. Now, in one of the videos that I posted on Iconestoga, it explains using an animation, why is it that, how is it that the electrons are going to behave looking at an animation? I can tell you verbally and showing you this PowerPoint, but I think it's way more beneficial when you can watch an animation, because you can see the electrons in real time and the holes in real time, how everything is moving inside the semiconductor material. But in this instant, you can see that if I apply a positive voltage here, and I apply a negative voltage here, okay, here we have the negative. Because we have two diodes connected like this, pretty much back to back, okay? There's going to be developed a potential barrier right here on that side of the semiconductor material, because we might say, okay, listen, the electrons are going to be pushed because we have an excess of electrons. They are going to be pushed in this direction, but because we have a positive material here, okay, yes, the electron would try to travel through the positive, but they would be rejected by this negative N type. Because now when this becomes so negative as well, because this is negative also, then it would be creating a rejection point, and that causes the SCR, when the SCR is connected between the positive and the negative without any signal to the gate, this just creates a huge potential barrier, and it doesn't allow the flow of electrons or the flow of charges. The reason why we have a gate here is because the gate is going to allow, like when we pass a small current through the gate, then the gate is going to be allowing us to overcome that potential barrier and to produce a full flow between the positive and the negative. Now, the advantage, I want you to remember that in the case of the transistor, And let me put it here. Whenever we had a transistor, when we had on the transistor, uh, that lead here, we call it our, like if this was a PMP, an NPN, I'm just gonna use an NPN as an example. I want you to remember that in the case of the transistor, that side, which is the, do you remember how we call that one here? The emitter is connected to the ground. On the top, we have the collector that was connected to a positive terminal. And then here we have the base, which is a reference voltage, which is connected also to a small positive voltage. Now, this SCR is behaving pretty much the same way like a transistor. The difference is that in the case of the transistor, you always need a constant voltage between base emitter, because with the voltage between the base and the emitter, you are going to have a current that is going to allow you to have a huge amount of power flowing between collector and emitter. So with a small control current, we were able to control a huge amount of collector current. That's the basic principle for the transistor. When it comes to the SCR, the advantage is that yes, we are going to be able to control a large current, okay? But now, on the gate, instead of having a continuous flow of base current, on the gate, we only have an input signal, an initial input signal that doesn't have to be there all the time. As soon as the SCR is, is closed and it starts conducting current, it's gonna continue to conduct current as long as is above the holding current level. Okay, so I just introduced a new term here, holding current. What is the holding current? It's going to be the current that is required for the SCR to continue to operate or to continue to work without having any gate input. So to put it in simple perspective, this is what's happening. Actually, I'm gonna wait so we can see it with another slide that I have already had, so I can explain a little bit more about that, excuse me, about that concept, okay? So now, let's keep moving. Like this is the symbol for the SCR, and I already told you, we have the anode, the cathode, and the gate. So we'll keep moving, and the SCR are usually used for high power applications. Like in the case, one thing that you are going to be able to see on the video that I posted is that it is being used for high power transmission lines, because in the case of high power transmission lines, you take the power from the hydro dam station, or from whatever source that you have, and you convert your three-phase into DC with SCRs. And once you convert it into DC, you can transmit it over long distances. And that way you only have to use 2 wires, that's number 1. And number 2, you avoid a skin effect. Remember what is a skin effect? Because of frequency, okay, like that circle that you see that I draw at the bottom, let's say that that is a conductor. Because of frequency, in an AC circuit, your electrons are going to travel around this area here, okay, on the outer surface of the conductor. So all the other area in an AC circuit, the center core of your wire is not being used by your current, by your electrons. Why? Because that's one of the effects of transmitting power with AC. However, when you have a DC transmission line, and that's what you get to do with the SCR, then the electrons will travel completely inside the full conductor. So what's going to be the advantage? Number one, you are going to transmit the same amount of power using smaller gauge conductors. And number two, you only need to use 2 conductors instead of using 3 conductors, and that translates into a lot of saving of like lighter power transmission lines, lighter conductors, lighter insulations. Everything is going to be less because you eliminate the use of 1 conductor. And that's one of the great advantages of using DC for transmission power rather than using AC. And the hero in the equation is the SCR. Okay, so that's why that we study the SCR in level 2 electronics. Any questions so far? Also, you are going to use it for a lot of other devices like DC, okay, like the DC drive. You are going to use it for DC drive. You are going to use it for AC drive in level 3 electronics as well. So it's being thoroughly used in industry nowadays, but they are mainly used for high power applications. If you don't have any questions, then we're gonna move ahead. Okay. So in this example that we have in here, this is the same thing that I just built on multi-sim. You have your power source. In my case, I decided to use 12 volts instead of 200 volts, but I'm just gonna give you a quick explanation on what this schematic diagram represents. As we said before, or as I said before, right here, right there, we have the anode. And right there, we have the cathode.
I promise to bring it back down.
Okay.
If I eat upstairs, I promise to bring it back down.
And then we have the anode and the cathode. And then this normally open push button, what it's going to do through the resistor, the reason why we have a resistor here is because that way we can limit the current to the gate, because the gate has a trickle current, which is usually very small, usually between like 2 to 10 milliamps. That's going to be your trickle current. So you are going to need to have the following is going to happen. As soon as we have a small trickle current in this direction, and I already said that that trickle current is going to be roughly about 5 milliamps. Okay. That's going to close pretty much the anode cathode is going to close, or is going to put in conduction our SCR, and then the SCR is just going to behave as a closed switch. The reason why this is a normally open push button is because you only have to push once and then you let go. Of course, you don't have to be holding all the time. And as soon as you do that, we are going to have a conduction. We are going to have like a flow of current through the load. Now, that current will continue through the load until the only way, in our case, that we would be able to pretty much like turn off the SCR is by reducing the holding current. Your holding current is usually like in the case of this PowerPoint, it says it's going to be 100 milliamps. So as soon as we reach 100 milliamps here, as soon as this becomes 100 milliamps or less, then the SER is going to stop conducting. Okay.
So can I ask a question?
Yeah, sure.
So what? Oh my God.
What happened?
Sorry, fucking dryer's going off. So the whole point of that, what is so that way you don't have to have such a heavy duty switch to get the current flowing in that circuit kind of deal. Like you just have to have a a switch that can handle the 5 milliamps, and then that allows the current to flow through the SCR, so you don't have to have like a huge heavy duty switch on the circuit, or what?
Yeah, perfect. That's like in the case of DC, that's going to be pretty much the point. That way, because you don't have the heavy duty switch, as you just mentioned, with a very small control current, you're going to be able to pretty much make this work without having any additional losses, like in the case of a transistor. Like in the case of the transistor, because you need a second constant source of power, like if you were going to use that instead of using an SCR for large amount of power, then because you got to have a second source of power, that's going to be a loss that you have to account for. In the case of the SCR, you are completely right. You are going to be able to pretty much operate it as a switch with very small losses.
Okay.
Yeah.
Thank you.
That is correct. It looks better, you know, like once we get into, I was going to say, like once we get into the AC, then it looks even better. It makes even more sense the way it works. Okay, so let's get moving. So in this instance, I have pretty much the same thing. Here we have something that you got to keep in mind, okay? Like in the case of an SER, and in the case of any electronic components, we always have a small, let me run this simulation. We always have, you know, some kind of leakage. Always leakage is going to happen. I want you to notice the following. In this instance, I have here a variable resistor because that's how I'm going to be able to reduce the holding current through the SER in order to be able to turn it off. Okay. Now, at this point in time, because the SER is off, the SER is pretty much taking the full voltage through it. Okay. So the SER, as you can see, is behaving as an open switch. Remember that in theory and in reality, when we have, if I substitute this SCR for an open switch, I would be able to see the same 12 volts through the open switch as I can see through the SCR. Okay, so in here, I am using a current limiting resistor because I don't want to apply too much current to the gate for fear of burning the gate. If I put too much current through the gate, then it's going to burn out. So that's why I'm using this current limiting resistor. And then I'm using a normally open push button. Please, I want you to observe that here still we have a small voltage drop because we have some kind of leakage through the SER. It's not perfectly sealing everything. So we have a small loss, but it's not tremendous. It's not a tremendous amount of loss. Now, as soon as we close the switch, I want you to be able to observe what happened to the light bulb. Can you see how it changed to yellow? And I want you to observe now that through the SCR, we are going to have a voltage drop of pretty much 1 volt. And with 1 volt, because that's the amount of voltage which is required to overcome the potential barrier, now we have a light bulb, our load on. And yes, we can see that we have like whatever, 11 volts roughly. Also, you can notice here all current flow through the circuit. This is the amount of current which is flowing through the SCR. Like specifically on this one, our holding current is roughly about 10 milliamps, okay? So in this instance, it's a very, very small holding current that is required on this SCR. So, okay, guys, at this point in time, you see that we don't need to use the, I mean, like as soon as we press the push button, this light came on, and it's just, I mean, through the SCR, it's holding the current. What I'm going to do now is that I am going to reduce. I want you to be able to see. I want you to be able to see what happens through here. Okay, through here first, the current. I want you to observe the change in the current as soon as I increase the resistance, so I can reduce the amount of current which is flowing through the SCR. Because the only way, and listen to this, the only way that I can turn off the SCR is by taking the current through the SCR below its holding current level. Once it goes below the holding current level, the SCR is going to turn off, and this value is going to go back to your roughly about 12 volts. Until I don't turn it off completely, I'm going to be able to see a fluctuation, I mean, like a voltage fluctuation here and here, but this is not going to be telling you that the circuit is completely off. So let's see this. I have a 2500 on resistor. So you can see that the light went off, but still there's a flow of current. At this point in time, I still have 22 milliamps. As I said before, this SCR, this specific SCR that I'm using here, has a holding current of about 10 milliamps. So I'm going to continue to increase my resistance so I can continue to reduce the current flow through the SCR. And please take a look at what happens. Let's increase it a little bit more. You see, I'm still at 11.2 milliamps, and still it's on. That SCR, it's still on. And even when we have like whatever, like 0.6 volts through it, you can see that it's behaving pretty much just like a normal diode. Now let's increase just slightly this resistance all the way to 10 milliamps. Let's increase it a little bit more below 10 milliamps to see what happens. Still, it's not off. Okay, this one is 5 milliamps. At 5 milliamps, this SCR is gonna turn off. We're getting close. Still, it's not off. You can see that even at 5.34 milliamps, this voltage is still like this voltage here is still like 0.5. It's just behaving as a regular diode. Now, when we increase this resistor to reduce the current through the SCR even more, now look at what happens. Okay, as soon as I increased my resistance to a level where I was able to reduce my current below the 5 milliamp threshold, the SCR shut off. She shuts down, and then it was able to behave again as just an open circuit, or as an open switch. Any questions about that? Turn it on. And the way to turn it off is here. Okay. So any of these circuits that I make here, like I know that it takes time to get used to multisim. Any of these circuits that I built, like if you want me to send you the copy of it, so you can play with them, I mean, that's not a problem for me, okay? I can send you the copy anytime. Now, we are going to see the same circuit now using, can you see that one there? The new demonstration.
Yep.
And you can see it perfect. So the reason why I sketch, well, I didn't sketch anything, you know, the reason why I just put together this other demonstration in here is because I want you to be able to see the same thing instead of a push button. I want you to be able to see that once we have the right trigger current, then we are going to be able to make the SCR, we're going to, I mean, cause the SCR to start working. Under normal condition, I'm gonna, okay, let me shut down the other simulation so I can run this one. In this circumstance, you can see that my LED in here, I'm using an LED. And because these are very, very sensitive probes, still we have some leakage. You can notice here that we have 4.84 microamps. So that's the amount of leakage that we have on the SCR. You may wonder if there's any component, any solid state component that don't have any leakage. I mean, like that would be pretty much impossible. Things are always have some type of leakage, but usually the leakage is so small. The leakage is so small that I mean, it's not really like something that is going to be like doing any damage or causing any like bad behaviors in the circuit. I got a question here that it says that it's a variable resistor. If that is the typical way to reduce the holding current. Sometimes it's not just a variable resistor in order to reduce the holding current. Sometimes you are just going to have like something that I could use instead of a variable resistor would be just a normally closed contact. Like in this instance here, I have a normally open contact. I could put a normally, instead of a variable resistor here, I can use a normally open, a normally closed contact. And that way, you know, by opening the contact, I could shut down the SCR, just like you do in motors controlled circuit. We could do the same thing in here, okay? What would be the difference? That instead of using a relay, now you are using an SCR to perform the same operation. And instead of using like contacts that are moving and things like that, you would be using, I mean, like you would be using with your contact an SCR to substitute the relay and the contacts themselves. That would be the great advantage. Did I answer the question or? Okay, so now, in this instance, guys, when I'm running the simulation here, all I want you to be able to see, I want you to be able to see that once the gate reaches the trigger current, so I introduced two terms here. One that is called trigger current. The trigger current, it is the current required to turn on the SCR. Please keep that in mind. Trigger current, it is the current required to turn on the SCR. And the holding current, it is the current that is required to keep on the SCR. Okay, so let's get moving then. You're most welcome. Let's keep moving. So in this instance, we can see that the same situation is happening. The SCR is behaving as an open switch. Still, we have some leakage. And because I have a very, very high resistor here, yes, we are going to be able to observe that we have some voltage drop between the 100 ohm and the 2.5 kilo ohm resistor. Now, what I want you please to notice is two things. Number one, I want you to be able to see how, as I reduce my resistance, I have a 20 kilo ohm resistor. As I reduce this resistance, this current is gonna increase. And when this goes to roughly about 2 milliamps, then the SCR is going to turn on, okay? Once it turns on, it's gonna be taking a very minimum amount of voltage, roughly about 1 volt, to operate our load, which in this case is going to be our 100 ohms resistor, which is together connected with an LED. So let's see that. I'm going to start moving. I'm going to start sliding or reducing this resistance. You can see that as soon as I start reducing the resistance, I want you please to notice how the current starts to go up. But that current is not enough to turn on the SCR because you can notice right on the top that the voltage, it still is 10.39 volts. Okay, so I will continue to reduce this now to 80, to 60. I'll continue reducing this slowly. I am already all the way up to 1.90 milliamps and still is behaving as an open switch. 1.36 milliamp and nothing. 1.58. 1.88, still an open switch. Now, as soon as we get, did you see what happened there? As soon as we got, we were not able to see that we got to the 2 milliamps because as soon as we got to the 2 milliamps, this LED was able to turn on. Okay, I'm going to show you that once more. I'm going to turn it off. I'm just going to show you the last part. Okay, so let's look here. You see that we have 1.36 milliamps. Can you see there? Now we have 1.58 milliamps. Okay, so that's the amazing thing about the SCR, guys. With such a small control current, like in the case of that specific SCR, it's gonna be 2 milliamps. With just 2 milliamps, I'm gonna be able to, with just 2 milliamps, I'm gonna be able to control this huge amount of current, which is gonna flow through here. So let's just get above the 2 milliamps. And we're not going to be able to see the 2 milliamps, as I said in there, because it's going to turn on right away. And then once it turns on, it doesn't require the 2 milliamp current to continue running. Okay. As soon as we did that, the SCR is on. I can slide this back all the way up to the max value, and this will continue to be on. And then now with just 2 milliamps, we were able to have a controlled current because of the load that we have connected of 94 milliamps, which would be considered a huge gain. But we don't really get into the word gain because this is just behaving as a fixed switch, okay? As a switch, which is being able, which is controlled by a small trigger current. Any questions about this one?
Yeah, doesn't the holding current have to be over 100 milliamps? I thought you said the holding one had to be over.
Yeah, but remember that was, I told you that was on the slide.
Oh, okay.
Yeah, on the actual slide, and I'm gonna show you that in just a moment. Let me just show you that. On the actual slide that you have in here, they are using 100 milliamps as an example, just to make it easier. Okay, let me advance this a little bit more.
Oh, okay. So the SCR will say on it what its holding is, and
Yeah, so not all SCR I'm going to have the same holding current. So not all the SCR are going to have the same holding current. That's only on the slide that we have in here. Let me go back to that one.
So it doesn't work like a diode where it's 0.7 or 0.
It's going to be working like in the case of it's going to be working as a diode when it comes to AC, and because it's going to rectify voltage. So was that your question? Sorry.
I think we're thinking that maybe they had a specific value like a diode does of 0.7 or 0.3.
Oh, you mean like the voltage drop, the 0.7 volts is the voltage drop on the diode that you have to overcome the potential barrier. The 0.7 volts, it is the natural migration of the potential barrier, the natural migration of the electrons that happen inside the PN junction. That's your 0.7 volts. It creates that 0.7 potential difference right at the border between the P and the N junction. Like in the case of the SCR, you have the same thing. Actually, in the case of the SCR, let me get back to the PowerPoint so I can show you this. But you are going to be able to see that on the video that I shared with you, and it's going to make way more sense. Like in the case of the SCR, can you see that PowerPoint? You are going to have a 0.7 volt potential barrier here on that edge. Can you see that slide that I'm trying to share with you?
Yep, I got it.
So you are going to have 0.7 volts here, 0.7 volts here, and 0.7 volts here. Okay?
Yeah.
So like, because you have so many different potential barriers, that's why when you apply your positive and negative here, nothing's going to happen unless you trigger the SCR.
And
In other words, what you are doing
SCR will
when
have
you
a different
trigger the
value for that.
SCR, when you trigger the SCR, what you are doing in simple terms is that you allow a huge amount of electrons to come here, and this becomes a huge negative, and that by causing this to become a huge negative, that way it just behaves as a regular diode. Kind of make sense?
Yep, sounds good.
Yeah, because that way you eliminate these two potential barriers once you introduce a signal there. The good thing about it, I'm glad to hear that it makes sense. The good thing about it is that we are going to be using a very small current to eliminate the two other possible potential barriers and to cause the current flow through the circuit. Now, guys, before we end, I just want to show you one of the most important concepts of the SCR. We can use, I want you to see this AC circuit. Now I substitute the 12 volts DC by 60 Hertz, 12 volts RMS. In this instance, I'm going to be doing the same thing. At first, I'm going to have, I'm not going to trigger the SCR. It's going to be off. And I want you to be able to observe what's going to be your current. And I want you to be able to see as well the following. I want you to be able to see the voltage. I mean, what's going to be your voltage? Stop this. Okay, like through the load. And also we are going to open the oscilloscope. And I want you to be able to see also in this case, is going to be the rectified voltage through the load. Because your SCR, when connected to an AC source, is going to be able to behave as a voltage, as a dimmer. Let me put it that way, okay, as a voltage regulator. Now, why that's going to be happening? In the case of AC, remember that AC is going to go all the way up. Let me get this here. AC is going to go all the way up here and then down, and then it's going to change direction, right? Now, in the case of AC, let's say we are going to have 6 volts here, okay, 6 volts of effective value here, 6 volts of effective value here, and that's why we have 12 volts. Fair enough? At the same token, you can see that, by the same idea, you can see that we have connected to the same terminal the anode and also the gate. They are connected to the same exact terminal. So whenever this, I want you to be able to observe that whenever this current reaches like a high level, like in this case, it reaches the 2 milliamps, immediately the SCR is going to start conducting, and it's going to conduct the positive pulse, but it's going to block, because it's a diode, it's going to block the negative pulse. Now, as soon as the SCR, gets to this point, as soon as the current through the SCR gets to this point here, to 0, the SCR is going to shut down. So it's not going to be on continuously, because you cannot keep your holding current at the same level all the time like we were doing when we have DC. I'm going to run the simulation so you can see this. Right at the beginning, you can see that we have what? Just a normal halfway rectifier. And you would say, so what's the difference? Like, I don't see anything difference between this and a regular diode. Now I'm going to show you the cool part. Okay. So I want you please to notice the following. I want you to notice where, or the position of where the signal starts. This is going to be my starting point right there. Okay, now let me use something to indicate that point. Okay, maybe not the best. Move it here down. So please notice that. That's going to be all the starting point right there. As I was telling you before, here in this instance, I have a variable resistor. Right now, my variable resistor is at 0. So what is happening is that the SCL is being triggered, and because it's being triggered, it is allowing the full signal to go through. As soon as I start to increase my resistance, I want you to be able to observe, as soon as I increase the resistance to the gate, I want you to observe what's happening to the output voltage right there, where I have my cursor. Right now, we have a rectified voltage of 4.98 volts. Let's see what happens. I'm going to increase it to 5%. I'm going to increase it slowly. 10%. Has anything changed? Not much, right? Now we start to see a small fluctuation. Okay, I'm going to increase it to 40% there. Okay, let's keep it at 40%. Now that this has been, not that much, 35%, I'll just keep it at 35%. So I want you to observe the following. I want you to see how the position have shifted. You see that I didn't touch the oscilloscope. However, the position of the sine wave my rectified voltage, which is my pulsating voltage, have changed from the initial position and have shifted slightly, right? Also, you can notice how is it that the output voltage has been reduced slightly. We have lost about 200 millivolts. Now, why is that happening? That is happening because by introducing a higher resistance through the gate, now we are delaying the firing sequence or the time when the SCR is supposed to start. Okay, so if I continue to increase, look at there, it was a little bit more dramatic. As I continue to increase my resistance, then I continue to reduce my output voltage. And I want you please to observe how the phase is shifting right there. Okay, we are reducing pretty much. We are changing the shape of that signal because we are making sure that the SCR starts to work right at that moment. Okay, this is when the SCR starts to work, and that's why you see a straight line from 0 volts all the way up. And by doing that, we were changing the average value of my DC signal, which is my DC output. Look at that, guys. So as I continue to reduce my voltage. Now I turn it off, right there. So at this point in time, we can see that we were able to reduce our current. Of course, if voltage goes down, the current is gonna go down. Voltage goes up, current is gonna go up. But if our voltage is down, like in our situation, then of course our current is gonna go down. Voltage down, current down, Ohm's law. But I think this is the most beautiful thing, you know, just to be able to see it. We say see, because you were able to see that because we change through the resistor, we change when we can turn on the SCR, we were able to pretty much control also on the AC circuit, we were able to control the output voltage. And that's one of the most fundamental applications of the SCR, you know, to be able to control the output voltage of an AC source. Any questions about that?